2011, number 2 with a TI. Okay, so I have a pot of tea that is cooling, and the temperatures are given to me over this 10-minute time frame. Part A, use the data in the table to approximate the rate at which the temperature of the tea is changing at 3.5 and show the computations. If we are approximating a rate, we are approximating a derivative. A derivative is a slope. To approximate a slope, we're going to do slope of the secant. So for 2A, I want to do the slope of the secant. I'm approximating for 3.5, so I'm going to use my values from 2 to 5. I set it up, and my approximation is that the rate is negative 8/3 degrees Celsius per minute. So that's part A. Part B, using correct units, explain the meaning of this in the context of the problem and use a trapezoidal sum to indicate and approximate that same integral. So first thing I want to do is explain the integral. Because it has the 1/10 out in front, it's the average temperature in degrees Celsius over the first 10 minutes that the tea is cooling. And now I want to do my trapezoidal sum. So I'm sketching out the points that are plotted to find the area of each trapezoid. 1/2 the height, which is actually the distance on the x-axis, times base plus base. The bases actually come from my y coordinates. So I find the areas of all the trapezoids, and you don't want to forget that you have to multiply it by 1/10 because we want the average. So my final answer, 52.95 degrees Celsius per minute. That's part B. Part C, evaluate the integral of h prime and using correct units explain the meaning. So for part C, if I integrate h prime from 0 to t, I get h of 10 minus h of 0. Well, h of 10 is 43, h of 0 is 66, and I get negative 23 degrees Celsius. What that tells me is that the temperature drops, negative 23 degrees from 0 to 10 minutes. Not too bad. And then finally, part D. At t equals 0, biscuits with a temperature of 100 degrees are removed from an oven. The temperature of the biscuits at time t is modeled by a differentiable function b, and we are being given the derivative of b, okay? Using the given models, at t equals 10, how much cooler are the biscuits than the tea? This is the rate that the temperature is changing for the biscuits. So I want to find the temperature. So here's the thing. I want to find the temperature at 10, which means I want to integrate b prime. But if I'm integrating, I need limits. So I'm going to use 0 and 10. Why am I using 0? Because I have information on it. So if I look at this, if I integrate from 0 to 10, b prime of t, well, when I integrate b prime, I get b of my upper limit minus b of my lower limit. Now, all of this right here, I can put on my calculator. B prime is the equation they gave me. I'm going to integrate that from 0 to 10 on my calculator and get negative 65.817 equals b of 10 is what I'm looking for minus b of 0 is 100 that was given to me. Add 100 over, b of 10 is 34.183. That is not your answer. They want to know how much cooler are the biscuits from the tea. This is the temperature of the biscuits after 10 minutes. The temperature of the tea after 10 minutes is 43 degrees. That comes from my table. So I want to find the difference in temperature. Subtract them. The biscuits are 8.817 degrees Celsius cooler than the tea. That's your final answer for part D.